So this is my last lecture that focuses just on principal component analysis. It's a tool that we're going to use kind of for reference later, so it's hopefully worth having spent a fair amount of time understanding it with some depth. In this lecture, though, we're just going to do a little short discussion about interpretation of the principal components, how to understand vaguely or quantitatively how they relate to more familiar quantities. That'll include, of course, our familiar geometric picture that we've discussed a bunch. But a couple of other tools as well. We'll just sort of outline what they are. And then we're going to finish off by talking about kind of some warnings or pitfalls, telling you, this isn't everything. Principal component analysis, it's not magic. It doesn't solve all your problems, and sometimes it can create troubles that you might not be aware of. So the discussion is supposed to just sort of point out some of those dangers and pitfalls so that you'll be aware when they're around. I should also mention that you won't see my face in the corner of this lecture, as well as I think the next one. There was a glitch in capturing that feed, and so I don't have it. But I'll be back, I think about 2 lectures from now, where the glitch is gone and I've got the headshot back, and I'll be back there in the corner again. Okay, let's get started. We have the main picture, I think, for how you interpret the principal components, and that is, suppose these are the axes of the original data, and so maybe we'll call these like original variate 1, and original variate 2. So those are the columns of the X matrix in a 2-dimensional case. And then the principal components we can draw on here. And again, this is as if I've centered the data. So this would be like principal component 1 maybe. And principal component 2 be off like this, perpendicular to it. And we've talked about these little unit vectors that point in the direction of the principal components. So I call that guy alpha 1 hat. And the one that points along principal component 2, we call that alpha 2 hat. And so those are just dimensionless unit vectors that point in the direction of the principal components. And I think that's a pretty good picture for how you interpret what these things mean, and it'll help us going through. So let's just look at the 3 main tools that you'll have to interpret these things. So we're just going to look at 3 main tools. The first of them is just to look directly at the components of the alpha vectors. So we'll say components of alpha hat I, or maybe you want to say the components of the elements of the matrix A transpose, the matrix of loadings, or maybe you want to look at A by in the form where the vectors are in the rows. And so let's look at that. So the matrix A, if we look at row I column J of that, it's going to be row I column J of a matrix that has these unit vectors alpha 1 transpose, so that makes it a row vector, and then down to alpha p transpose. Whereas we've seen, and so we're talking about row I column J of that matrix, and we've seen that P is in principle, it could be the number of columns that were in the X matrix, except as we saw in the case where there's sometimes situations where you analyze data where you have far more columns than you have rows, and then P is not going to be the number of columns, it's going to actually revert to the number of rows. So anyhow, so this is the matrix of loadings, and what I wanted to talk about is looking at row I, column J of that, is looking at the projection of alpha hat I onto the original variant J, right? Because it's element or component J of the alpha hat I vector. So that tells you how much the alpha hat I vector points in the direction of the original variant J. And in the notes, you'll see this called alpha ij. So without the hat and with an understanding of what the I and the J mean. That's how you'll see it treated in the notes. And so the simplest way to kind of interpret these things when you just look straight at them is just from this picture, and just as we've said, it's really just kind of this thing here, which is that you say, if one of those things is big in absolute value, if alpha ij is large, and what we have to say what we mean by large, right? So large means compared to something. Compared to what? And let's just write out the two things that we've seen so far. Oh, I want to move that picture down a bit. So hold on a second. There we go. So we'll say if alpha ij is large compared to something, and the something here is one of two different things we've offered you. So it's either just 1 over the square root of p, and that's the sort of geometric criteria. We didn't name it that, but it's a good name for it. In other words, that's kind of the scale for what qualifies as big for these components. Or the other one was Mardia's criteria, and that was 70%. So 0.7 times the largest of the components of that particular vector. So this one was kind of called Mardia's criteria. Yeah, so these are the two different things we've seen for how you determine what qualifies as big for these components. But in any case, if one of those things is big, and again, I want to refer back to this line here, which I think is what was really important. We're looking at the projection of that principal component unit vector onto the original variant. And so if it is big, then what you say is that that principal component is similar to the original variant, right? So we'll say then the principal component for that vector, so PCI, is similar to the original variant J. Right, so that's one sort of obvious way to interpret these things. You can just look straight at the matrix of loadings and kind of understand what is the meaning of the different principal components that you've come up with. Right, so that's one way to kind of interpret them. The second tool is actually pretty similar, but let's just describe it anyways. It's sometimes used, and this is the principal component, original variant, and so let OV, I think I only used this once, but we're going to say this is OV for original variant, correlation. Right, and so for this, you imagine constructing some matrix Cij, and this thing is the correlation of column I from the X matrix and column J for the Y matrix. All right, so just to be clear, Xi in this case means column I of X, and similarly Yj is column J of Y. I think we used that notation for the Y matrix before, but I'm not sure if we did so for the X matrix. So I wanted to make sure it's clear here. But so this is just looking, you make a matrix of the correlations between these two different columns to try to understand how they relate to each other. And this is ultimately, it's really, really similar to the first tool. So very similar to the first tool, so to 1. And it's so similar, in fact, that these values in the matrix Cij, they're actually just proportional to the alpha, and I think you have to swap the row and column here to go to the transpose version. So they're actually just proportional to those components of the eigenvectors. And the proportionality, you could work it out. It's different depending on how you computed the principal component analysis. So the proportionality constants depends or is different for the two different types of principal component analyses that you might do. So for unscaled, and when you do unscaled PCA, that means you're using sigma, the covariance matrix, so that those alphas are the eigenvectors of the covariance matrix. Or for scaled principal component analysis, where the alphas become the eigenvectors of the R matrix, the correlation matrix. So when you do that, you get different results for the proportionalities here between this correlation principal component original variant correlation matrix and the principal components. You get different you get different proportionalities between the matrix of loadings and this correlation matrix. But they ultimately kind of tell you the same information. They're just off by a scaling. So the other thing you can do, which is relatively straightforward but kind of open-ended, is you can treat the principal components as a whole new space and start to explore it, start to explore new information. So treat principal components as new space. So that is to say, you start making plots with things along principal component 1 and principal component 2 and 3 and so on. And then maybe you start to add new variants and start to add columns and do formal kind of analyses like more correlations and stuff like that. So you can incorporate new external to X, previously unexplored variants, say. So we'll say external to X variants. You can do various calculations, so you can calculate correlations, etc. Or you can just make plots and see where the things land. Okay, so those are the three main tools for interpreting the principal components. And now we'll finish off today, again I want to move that picture down a bit, with just some sort of discussions of the weaknesses of principal components. So the things that might be problematic. Add one more page here just to be safe. Right, so it's a good thing to think about what could really go wrong. And this is actually the origin of that quote in early, I think it's at the top of the module handbook or syllabus. And this is just to say that principal component analysis is not really a magic wand, and you should be aware of its limitations. So not a magic wand. That is to say, you don't just get your bundle of data and just start throwing it through principal component analysis and think that you've done everything that can be done and that all problems are resolved now. You've gone into this magical space where everything is perfect. It really has a lot of limitations, and there are things you should think about. So these are going to be a small set of like sort of problems and solutions. So PCA, problems or issues. PCA's problems. And sort of some solutions. So we'll say approximate solutions. They really aren't full solutions though, and these things should be thought of as kind of cautionary for the most part. Okay, so I think how many of these am I going to go through? I think I'm going to go through about 5 of these, maybe 4, looks like. So the first one, these reduced space plots, the plots when you just look at a few principal components. So maybe you have 10 variates originally in your X matrix, and you start to try to analyze things in just 2 dimensions, the way we've actually done that in our examples, and I think you do it in your practical this week. So these reduced space plots, which are nice because they allow you to kind of visually explore things in a way that you wouldn't be able to do in 10 dimensions or something, or higher, or 100 dimensions. So reduced space plots, they risk excluding really important space. So whole dimensions are suppressed, and while in principle that's kind of good, that's the whole point, it could be that you actually are missing some important stuff. So I'll give you as an example the data from the Pima Indians, the Pima Indian obesity data. Not sure if that's how you spell obesity. Close enough for today. And this is what I had these figures for below, so I'm going to grab them and move them up. So these figures, in case you've forgotten, so where are they? They're down here. I'm just going to grab this guy. Maybe shrink him a little. So this is the Pima Indian data for the first 2 principal components, right? So this is a reduced space plot, because I can't remember how many variates that data originally had. This was one of the, this is a genetic data thing where we actually had a large number of columns in the X matrix, and when we did principal component analysis, it was reduced down to 40 different principal components, I think, or 39 or something like that. And here, if you were to have naively tried to do this as a one-dimensional problem, which I'll admit is really particularly naive, not many people would try to do that, I think. But let's suppose you just looked at this axis here, right? And then, so these are lean people or lower weight people, and these are obese or overweight people. You can see that along principal component 1 here, so just draw that axis up here as well, right along the actual 0. There's not a lot of discrimination between the lighter weight people and the heavier weight people. They sort of are kind of not exactly equally distributed along that axis, but not hugely separated on that axis, right? There may be a little bit. PC1 might tend to be larger for overweight people than for lighter weight people, but there are lightweight people that have large principal component 1 values, and there are obese people that have low principal component 1 values. So it kind of doesn't really discriminate. But along principal component 2, there is very clear discrimination. The obese people are at higher values and the lighter weight people are at lower values. So it's very clear, or much more so, clear discrimination, difference there. And I just want to bring to your attention, of course, you wouldn't really look at this. You would never have really, I think, been tempted to look at this problem in this way because of this plot here, which I'll just put right below it. I think I have to go, yeah, like that, right? So here, I'll just summarize here. PC2 seems more important. So if you had reduced your space down to 1 dimension, which granted is a little bit silly, if you had done that, you would have missed this. You would have missed the fact that you had one of your principal components separated out, the obese from the lean. And of course here I want to just draw your attention to the fact that you probably wouldn't have done this, right? Because here are the two different, this is principal component 1 has variance up here around, I don't know, 900 something. And principal component 2 is over here at, I don't know, around 700 something. And so you probably wouldn't, and you can clearly see there's like the scree type stuff is not until way over here. So you probably wouldn't have used less than this many principal components, depending on what you're trying to do. But nevertheless, if you just look at these reduced space plots, you might have missed this effect. And so it's pretty important to realize that when you do these reduced space plots, you really can actually be missing things. And here you could have done so. So is there a solution to this? Yeah, sort of. Okay, so just like I was saying, these are sort of solutions. So what do you do? Solution. It's not really a solution, but it's a kind of an approach. So in reduced space plots, in the reduced spaces, try not just the top couple of principal components, or try many combinations. Sorry, make this big again. Of principal components. So maybe look at like PC1 versus PC2, or PC2 versus PC1. But then maybe also look at like PC3 versus PC2, and so on. So see, you can still look at these reduced spaces, but don't just stick to the hierarchical or ordering of the principal components. Look at some of the other ones as well, and see if something really useful might have been just around the corner. Okay, the second kind of limitation that I want to address today is that the main principal components might not actually be important. So main PCs, and what I mean by main is like the lowest, like principal component 1 and so on, 1 or 2, might not be important. Right, so it could be the case that, so there's sort of two ways it could be that they're not important. So one way, for example, PC1 might be boring. Something that's already known. Right, so maybe it's something that you knew immediately should be correlated with obesity, or like think about the principle, or sorry, the Pima Indian data again. Maybe one of the variants was weight, and surely that's going to be strongly correlated with obesity and leanness, and so it's not something it's not actually sort of a new uh, thing that you suddenly can use to discriminate some new information. Really, it's not particularly exciting. So that's one reason why the lower principal components might not be important. They could be things that you already knew all about, and it's just not anything interesting or new. Um, the other thing is it could be the case that lambda 1, which is the variance along principal component 1, it might be totally due to uncertainties. So maybe whatever it is that went into measuring the stuff that produced principal component 1, maybe there was a lot of statistical error in those measurements. So this might be due just to measurement errors. Right, so if let's say one of the original variants was something that was particularly hard to measure, um, so that there would then be a natural large variation along the original axis 1 because it was a hard thing to measure, and that would lead to it being close to principal component 1. And it's not because it's useful, it's sort of the opposite. It's because not much was known about it. It was hard to measure that thing, and so it just had this wide variation. The last thing, the last version of this is that the overall ordering might not really be important. Of the variance of the principal components sometimes is meaningless. Right, and so as the example of that, let's suppose we've talked about this before, where you have like a data cloud. Let's say you have a data cloud that's sort of cylindrical in nature. So this is the data cloud. And this is just the three-dimensional case. So suppose your data is sitting in there, right? Something like this. Then clearly the principal components are going to look something like this. So number 1 will go along here because that's where there's the greatest variation along that particular axis. But 2 and 3, if it really is kind of symmetrically or it has this kind of circular distribution along that axis, who knows which way 2 and 3 might point. So principal component 2 might go here, or it could go over here, but let's just say that's principal component 3. But if that boundary that I've drawn here is really close to circular, then there isn't really much reason to think that principal component 2 is much different than principal component 3. So this is just something to kind of be aware of. And the easiest way to spot it is, this leads to some very obvious effect, which is that if you plot the variances or the eigenvalues, so there's I and lambda I, then what you see are similar values, right? So if this is, say, 1, 2, 3, 4, and 5. So I've only got 3 shown there, but maybe you have a bunch. Let's make these green, why not? So maybe 1 is big like that, and 2 is somewhere like that, and 3 maybe just barely below, and 4 barely below, and 5 barely below. If 3, 4, and 5 were all kind of suffering from this problem, which they call sphericity, then there's very little reason to have put principal component 2 kind of higher up on the scale than principal component 3, because they have essentially the same variation. And so the way to spot this issue, is to look for just similar lambdas. So the order is meaningless here. for not for principal component 1, but for principal component 2 and above, it's kind of meaningless. And so essentially what you want to do as your so-called solution, and this is really only a solution to this last bit, so to this bit here. Be suspicious of similar lambdas. Right, and so if you see principal component 2 has a similar variance as principal component 3, probably when you do your reduced space plots, you should look at PC1 and PC2, and then but also PC1 and PC3. So like in this case, you really should be looking at 1 compared to all 4 of the others, 2, 3, 4, and 5. Maybe you should be looking at 3-dimensional plots. That might help as well. But so this is not really much of a solution. It's just this is how you kind of spot this issue of sphericity. Look for similar lambda values. And when you see them, you know that there's not a whole lot of meaning behind the particular ranking of them. Okay, the next thing I want to talk about is outliers, and there's not a lot to say about these for me right now, other than just to beware of them. So outliers, they could do any of the following. So they might do the following. They might inflate or distort the covariance matrix. Right, so they could kind of spoil this matrix. If you have a collection of values which are really, really large, you'll get, compared to the others, you'll get some kind of really messed up values for covariances. And you can similarly inflate or distort the variations along the principal component axes. So there isn't a whole lot to say here other than just to kind of be aware of it, and maybe the so-called solution is just to try removing them to see what happens. Try removing. And here it's okay just to look. Right, we're really just kind of forming hypotheses with principal component analysis. So you shouldn't be too hard on yourself if you say like, oh yeah, look, I see these data points are really like they're about 1,000 times larger than all of their peers. Maybe let's just remove them and then redo the principal component analysis and see if some new insight appears, some better result. And then if there is a better result, then we can try to make sense of it even when the other guys are back in place, or we can reconsider putting them back or not. I don't know. But it's certainly okay to just try. I've many times been asked by students, what are we supposed to do with this outlier? I don't know if I can delete it or not. And it's good to be hesitant to remove data. You don't want to do that casually. But it's also fine to just remove it and take a look and see how it changes things, and then to go back and you just had a look to see what was going on. So don't be shy about trying that. Okay, and then the last thing I want to go over is sort of limiting assumptions of principal component analysis. And these are kind of big. So limiting assumptions. Right, so what does principal component analysis really assume? Well, I'm not sure if assume is exactly the right word here, but it sort of hopes or assumes / hopes that linear correlations or covariances encode everything. So it hopes that these are really the whole story of the data. But that is just often not the case. The world is not a particularly linear place all the time. And it could be that there are lots of important nonlinear relationships that you're not seeing. And so we'll just say that. So nonlinear relationships between the variates might really be there. And they won't really register. Or they may not. These are actually really common. Right? And I don't really have much of a solution to this issue. So I'll just say for this, the so-called solution, it's not really much of a solution at all. It's just to be aware of it. If you have some suspicion about what the actual nonlinear relationships might be, then you could create some new variate which reflects that. So like if you thought that there might be some particular importance to like the square of one of the variates, or the sine or the cosine of some variate or something like that, you can create a new one, a column that has that in it. And you've probably done that before with like multiple regression problems. And that might help you. But again, that requires that you kind of know what is the issue in advance. So these are just some of the concerns with principal component analysis. And you should just be aware that there are limitations, and some of them are pretty significant. So that does it for our discussion of principal component analysis. You could argue that we talked about it too much. There's quite a lot of lectures on it. But hopefully that'll come back as a benefit because we're going to use it to reference how other methods are doing or what they're doing, the details of how they work as we go along and talk about more things in the coming lectures. So in the next lecture, for example, we're going to do something totally new, which should hopefully be kind of refreshing and fun for you. We're going to talk about distances and similarities. So we'll introduce what that means and how this is useful. It's a totally different topic. Again, we'll be able to somehow reference back to principal component analysis a little bit. But it's a new topic. It has some sort of funky geometry involved, and I think you'll have fun with it. I'll see you then.